Okay, continuing our discussion on acids and bases. In this chapter, you will be learning what acids are and what bases are, mainly focusing on organic acids. So if you start with the definition of the Bronsted-Lowry definition, an acid is a proton donor. That means if you have an acid, it would have a proton associated with it, and according to Bronsted-Lowry, the base is something that can accept a proton, usually represented as B base. So in most cases, bases have a lone pair of electrons on them or a pi electron system to qualify for a proton accepting. So according to Bronsted-Lowry, the HA is an acid that can donate a proton, meaning H+. And a base is, according to Bronsted-Lowry, it is that can accept a proton. So these are the definition, one of the definitions. There are several definitions for acids and bases, but now we will just focus on those, according to Bronsted-Lowry, those substances that are acids and bases. Remember, the focus would be mostly on organic acids because this course is on organic chemistry, so that would enable you to classify compounds according to their acidity or basicity, as well as to see some reactions based on acid-base reactions. Suppose in a general category, an acid-base reaction can be shown as, if you have HA, the acid, and you have a base like this represented, if you just draw an equilibrium. Now, according to the definition, what we have already said is an acid is something that can donate a proton, or a base is something that can accept a proton. So if you just draw an arrow, this is the base of a pair of electrons that would accept a proton. So if you just take off that proton, that means all the electrons will remain on the conjugate base that would be formed. So the general reaction looks like BH, now a plus because it has already gained a proton, and A minus because all of the electrons that were on the proton are shared with the proton are left on the conjugate base. So the classification according to this equation would be: this is an acid, the original acid, the parent acid, this is the base, and the products also can be classified as conjugate acid or conjugate base. So this is the conjugate acid, and this is the conjugate base. So this is the general scheme of the reactions that could be existing between an acid and a base. So whenever you have an acid and reacted with the base would accept one of the protons on the acid, and you would create a conjugate acid and a conjugate base as products. So if you just have for example, if you just look at this reaction, an example, this is water molecule. Remember to have satisfied all the loose structure, so water has this formula. So if you just react it with something with this, with a negative charge, remember there is a negative charge on nitrogen. If you were to calculate a formal charge, nitrogen would have a negative charge because there are two pair of electrons. So this is an electron rich species. This is also, it has lone pair of electrons, but according to our definition, if we were to represent this as a base, this is as an acid, the proton is on oxygen. So this pair of electrons, like what we did in this, would take off that proton, and they will leave the negative charge on oxygen. So what would be formed would be, you have in the equilibrium, let's say this is the equilibrium that would be forming, would have N, H, right? So since it used to have a negative charge on it, now it would be neutral, plus OH with a pair of electrons left on it and a negative charge. Remember, whenever you do a chemical reaction, charge has to be conserved. The way that you'll check that your reaction scheme is correct would be if the charges are balanced actually. For example, here you started from a neutral species in both cases, no charge on this. So you have a plus and minus, so the products are also charge neutralized. Here we started with a negative charge on nitrogen. We took abstract or take off the proton because this is an acid-base reaction. You have now a negative charge overall in the product side as well as in the reactant. So this also is a proof that you have done a good job in terms of writing the reaction. So here the water molecule is acting now here as an acid. Here this molecule, the NH2 minus, is acting as a base. Here this is the conjugate base. Actually that's ammonia, conjugate base. Actually it's conjugate acid, sorry. That's which took the proton, so this is conjugate acid, and this is conjugate base. Now there is an important distinction you should remember here. All of acidity and basicity are relative terms, meaning that depending upon what reaction or what components they are interacting with, one time they could be an acid, one could be a base. That means based on the reaction, for example, here water is acting as an acid and the NH2 minus, the amide, is acting as a base. And you are creating a conjugate acid, ammonia. But ammonia in its general characteristics is it is a base. So you should remember what is the specific question that would be addressed would be mostly dependent on what reaction. In what reaction is the particular molecule is participating. So remember, you have an acid because that is the proton donor. You have a base because this is the one which is abstracting the proton or taking away the proton. And here, whatever is taking the proton would become a conjugate acid. Whatever is the proton donor would become a conjugate base in the equilibrium. So these are reactant side, this is product side. These are reactants, these are product side. Okay, giving you one more example for an acid and base pair in the reaction. For example, if you have HCl, which you know obviously a mineral acid, and it's reacting, let's say, in the presence of methanol. What would be the product? So the products, these are reactants. So this is the acid because it is carrying the proton. Here this is a base because we are assigning it to donate those pair of electrons, or to use those pair of electrons to abstract the proton. So the products are if you just move this pair of electrons, you need always to have a pair of electrons on a base. Those pair of electrons would take away that proton and would create as a product, that would be Cl minus right, plus CH3O. Now you have H on it, plus another H, and a pair of electrons that was already there. So this is the product what you see here, and in assigning which one is a conjugate acid, conjugate base, in this case this is the negative charge which is carrying the electrons after the proton has been taken away, would become a conjugate base. The substance that carrying the proton in the product side now would be a conjugate acid, because it has that proton on it. Therefore, its character would be a conjugate acid. Here you have a pair of electrons on it, so it would qualify as a conjugate base. In the next session, I will just show you how do we measure the strengths of an acid. How do we say a strong acid, a weak acid, a strong base, a weak base. So we'll discuss that in the next discussion. So in our discussion, we'll see how a strength of an acid is being evaluated by pK value, and the definition where we say a strong acid or a weak base or a weak acid would be defined as something, for example, which gives its proton very rarely would be a strong acid. Something which can accept a proton very easily would be a strong base. But there is a definition for how we evaluate the acidity strengths. Suppose you have water molecule again. Now water is acting to donate its pair of electrons, therefore as a base, and you are dissolving, for example, an organic acid or some acid species in the water molecule. So based on this equilibrium would be written as a pair of electrons would take up that proton. As I said, the definition of an acid is something which can donate its proton, and the definition of a base is something which can abstract a proton or take away a proton or gives its electron. So here, this is a base. Remember, like I told you earlier, the definition of an acid or a base is dependent upon what kind of reaction, or it's only relevant in the presence of a counterpart or a reaction. So here is an acid. So the product would be, now water molecule would accept one more proton, and it become a positive, and you would have A with a pair of lone pair of electrons and a negative charge. If you just look at this, you have a neutral reactant, meaning no charge, zero charge from reactant side, and from the product side a plus and a minus, which is also a neutral species in the product mixture. So here this is a conjugate acid, and here this is a conjugate base. So if you were to write an equilibrium for this, equilibrium constant for this, it would be K equilibrium. So that's how we measure whether that equilibrium is very large or very low. That would determine whether an acid is strong or a base is strong as well or weak. So the K equilibrium for this from your general chemistry would be, this is defined as H3O plus, let's say just shorten-handed, and A minus right, from the reactant over product. You have product over reactant. Now you have H2O and you have HA, which is the acid. So if you remember, since water is in large excess, we usually keep the concentration for water as unity, or 1 for a liquid, a pure state. So actually the equilibrium constant is written as, in a summarized way, where we give H2O is a constant concentration, which is unity, and A minus over HA. So this is the net equilibrium constant. Usually this equilibrium constant actually is called the acid dissociation constant, and we can also define it as Ka, acid dissociation constant, or the equilibrium constant for this reaction, which shows the dissociation of this acid, the weak acid, in water to give you a hydronium ion species and a conjugate base. So based on how easily this would leave its proton is what makes this acid a strong or a weak one. What does that mean? That means the concentration of the hydronium ion times the conjugate base, meaning the numerator, if it is a large value, over the acid value, which is the reactant side, Ka would be large. So something which has a high dissociation constant or ionization constant as an acid with high Ka value is defined as a strong acid. Something which has a Ka value which is very low, that means the equilibrium is not shifted to the right side, rather it still remains in the undissociated form, that equilibrium constant is low. Therefore, that is a weak acid. So the definition of a strong acid or a strong base is defined by the ease of, for example, the acid to donate its proton. For example, if this acid tends to give its proton very easily to the base, we call that a strong acid. And the tendency of this base to take the proton, if it is very high, that means the base has high tendency to take a proton, that would make it a strong base as well. So the definition is that something which is keen or very easily donating its proton to a base is a strong acid which has a large dissociation constant. So by definition, this is called the acidity constant. Acidity constant, meaning the dissociation constant for the acid. That acidity constant, in most organic acids, it ranges from 10 to the power of minus 5 to 10 to the power of minus 52. That Ka value ranges for organic acids. That is in organic chemistry. That's what we will be dealing with. The dissociation constant ranges from 10 to the minus 5 to 10 to the minus 52. The 10 minus 5 being a strong acid, stronger acid than compared to the other ones. So strong acid. This is weak acid. What does that mean? Substance that has a large Ka value, which is 10 to the minus 5, relatively is high for organic acids. That is a strong acid. And a weak acid would be 10 to the minus 52, very, very low number for its dissociation. So what it shows us, the 10 minus 52 tells us is the equilibrium cannot be shifted that much to the right side. Rather, it's mostly shifted to the left side. So it's undissociated acid because this ratio would remain very low. So remember, a Ball estimate figure would be a 10 minus 5 being a strong organic acid. This is for mostly organic acids, up to 10 to the minus 52 being very, very weak acid. So that is the extreme end of it. So this is how we measure the strength of an acid or a base. So usually, since the numbers are very large, whenever you just look at them in terms of rather than putting them in an exponent form, we usually can write this in terms of a pKa value. So the pKa value would be, if you just were to write the Ka value in pKa, it's just a logarithm value. So pKa, which is the same as measuring the strength of an acid, pKa is equal to the negative logarithm of the Ka. So this relationship would tell you that high Ka value would be very low pKa value, because you have a negative log K. Very low Ka value gives you high pKa value. So species that have high pKa value are weak acids, such as this one, and species that have a very low pKa value are strong acids. Let's calculate this. For example, pKa for a 10 minus 5 would be pKa equals minus log of 10 minus 5 equals pKa of 5. That is for the strong acid. How about if you look at for the weakest acid, pKa equals minus log of 10 minus 52. That would be pKa of 52. So remember, high Ka value is related to a strong acid. Low Ka value is related to weak acid. But in terms of pKa, just to rewrite it in a logarithm scale, it is the opposite. Low pKa value is a strong acid. This is a strong acid, still with 5. And this is weak acid. So Ka and pKa are opposite. So remember, large equilibrium constant, acidity dissociation constant, is a strong acid. Low dissociation constant Ka is weak acid. But if you are writing it in pKa value, low pKa means very strong acid, and high pKa value, like 52, is a weak acid. Okay, here I have some examples of organic acids. That means they have different pKa values, as you see on the board. pKa value of 10, 16, 41, and 50. So whenever we are assigning a pKa value, it means that it's measured and we know the acidity. This is the strongest acid, this side, relatively strongest, and this is the weakest acid based on pKa value. So if you look at the compound itself, I'm referring to the acidity of this proton, how easy it would be to donate that proton by a base. That means if there is a base, how easy it would be, or how easy this compound would leave its proton. So based on this scale, the pKa value of 10 is referring to that proton. The pKa value of 16 in this compound is referring to this proton. The pKa value of 41 is referring to one of these protons, and the pKa value on one of this proton. So if you just look at this, what it means is, if you have a pKa value of 10, it means if you have a reaction of this compound, OH, and if you have a base, because we have said this is an acid, the equilibrium would look like removing one proton from oxygen and a conjugate acid would be pH plus. So this is what the equilibrium looks like for, at least for this one. That means the fact that it can go at ease compared to this one would be this is a much more robust reaction toward the right side. So the equilibrium is mainly shifted as compared to the other one is shifted toward the right side. So that's why a pKa value of 10 means a Ka value of 10 to the minus 10. So when we say pKa value of 10, we meant that the ionization constant, this is in log scale, is 10 to the minus 10. So the pKa value of 16, the second strong acid, is pKa of 16 for this proton right here, where it is attached to the oxygen. So this proton actually is more acidic than even CH2, CH3 proton, because it's already attached on an electronegative atom. So you should always look at determining the pKa value qualitatively by looking where is that proton actually. Why it would be making it easier for it to go or abstracted by a base. So pKa equals 16 is a Ka value of 10 to the power of minus 16. Much lower number than 10 minus 10. So that means that's why it's a weaker acid. The next weak acid, and that is the weakest acid. So these are some of the examples. You should remember to which proton you are referring to. The Ka value or the pKa value is very important. That means I am referring to particularly to that proton where it is on oxygen. Because if you have, we have, obviously there are hydrogens on this, one hydrogen on this, one hydrogen. These are not as acidic as the one which is on hydrogen. So one characteristics you should know or you should remember would be a proton that is attached to a more electronegative atom is much easier to be taken by a base than which is attached to a carbon. That's why, as you see here, these protons or these hydrogens are attached on a carbon, which is more electropositive than oxygen, let's say. That's why it's not very easy to snatch off a proton from such a compound, because the reaction being, so the reaction, for example, for that one would be CH3, CH2, CH2, no, CH3, that's 3 carbon. If you have a base on it, the base for it to take this proton is not very easy. That's why it's not that acidic. If it was very acidic, it really requires a very, very strong base for you to able to deprotonate or to take off the proton. So the equilibrium actually is much more shifted to this side than to be in a conjugate base form. For example, what we are suggesting is CH2, one of the proton is gone, and you have a pair of electrons there, and you have a BH plus. This reaction, as compared to the top one, if you take A and B, the reaction on A relatively would go very easy to the right side than the reaction in B, where the reaction is more favorable to go back. So this is a very weak acid, and this is a very strong conjugate base. So remember, this is very strong. If it is formed, it is very strong. So a very weak acid always generates a very strong conjugate base. So this is a conjugate acid, the acid. So remember, if the reaction to happen, if you always a weak acid would generate a very strong conjugate base, but the reaction is not most likely to go that direction. As I said, the ease of this proton to be taken by this base very low because it is a very weak acid to donate or to give off its proton. But things that are also attached to an electronegative atom like oxygen, relatively they are easier to deprotonate. That's why they are stronger acids. So these are examples where you need to exercise to estimate what would be the qualitatively whether they would be a very strong acids or not. Okay, continuing on pKa discussion, I want to focus on your attention to a pKa table that can be found maybe in any organic chemistry textbook or any table. So pKa tables are given, provided, but there is a way that you should qualitatively understand how to estimate pKa values. First, I want just to show you some numbers from a pKa table. Here, hydrochloric acid, which is the strongest acid, has a value of -7 because that is a very low pKa value, -7. So that is the strongest acid. This is strongest. And here with pKa value of 50 would be the weakest acid. And during studying the pKa table, you should also know which proton or which hydrogen we are referring to. For example, in hydrochloric acid, obviously there is only one proton. That's the hydrogen that would be abstracted by a base. So that's what we are referring to, pKa value of -7. Here, for example, I think we have, during a general discussion, we have such compound discussed. So this is acetylene, where this is sp hybridized carbon. So we are referring to this hydrogen where it is attached to an sp hybridized carbon. So the reason that it has relatively stronger acidic property is the carbon that is sp hybridized, if you remember in our discussion, the sp hybridized carbon has a more electronegativity character. So hydrogen that is attached on an electronegative atom is more acidic. So if you look at the relative number, this acetylene compound, where we are referring to the acidity of this hydrogen, it has 25. And hydrogen gas, to one of the hydrogens, we are referring to one of the hydrogens, is 35, so a weaker acid. Here we have NH3, which is ammonia. If we are referring to one of the hydrogens, it is 38. Here we have methane. This is a group of alkane. In the group of alkane, if we are referring to this hydrogen, it has a pKa of 50. That is the weakest acid. That means it's very hard to take off that proton from the acid. So if you were to look at what the conjugate base of these acids look like, for example, for hydrochloric acid, the conjugate base, when it is dissociated in water, it would give off Cl-. So these are the conjugate bases that after the proton was removed, this is what would be formed, if it forms. Obviously, for the strongest acid, Cl- would be created because it is a strong acid, so the dissociation or the proton can be easily deprotonated, therefore Cl- could be created. For the acetylene, the conjugate base looks like one of the proton gone, a pair of electrons would be here, this is the conjugate base. For hydrogen, if we are able to deprotonate hydrogen, the conjugate base looks like this, with 2 electrons. For ammonia, the conjugate base looks like NH2, one of the proton is gone. You have two pair of electron lone pairs, and the conjugate base looks like that. For methane, the conjugate base, it looks like this, with a pair of electrons. So remember what I already told you. A very strong acid would have a very weak conjugate base. So this is the weakest conjugate base as a base. Chloride minus is a weakest conjugate base. So don't confuse. This is the acid. If the acid was to react and give off its proton, you'll generate Cl minus, which is the weakest conjugate base. The next conjugate base, which is the weakest one, would be this, but the strongest conjugate base, if at all it forms, is this. So this is the strongest conjugate base. So I want you to practice one, reading the pKa table. The pKa table is already provided in most textbooks. You can find them. And to try to write the conjugate base of the acid and try to classify whether it is the strongest or the weakest conjugate base out of it. So remember to study, or generally to know where the ranges are. For mineral acids like hydrochloric acid, obviously you estimate to be very strong acid. But for alkanes, for example, it is 50. So there is a qualitative way of understanding pKa values for different compounds. For example, alcohols in general are 15, 16, around those numbers the pKa values are. So furthermore, I want to give you, for example, for this ammonia type, except one of the hydrogens is replaced by this ring. So the estimation is close to 38, as you see. So you don't have to memorize every compound, but something which is attached to a nitrogen like this is around 38, 40, around that value. As I already told you, something like alcohols, these are called alcohols because the hydrogen is directly attached to oxygen, as I said, 16, 17, 18, around those. You don't have to know exactly the numbers, but you have to qualitatively know what the group of chemicals would have, because it's not, we are not referring to this hydrogen, that hydrogen, we are referring to the one which is attached to oxygen. How about if you have compounds like this? Look at this compound. This compound is attached to oxygen, and that oxygen is attached to a carbon which is next to a double bond carbon oxygen. So it is very different from the other ones, and it's the strongest acid as compared to the three examples I gave you. So this is the strongest because pKa value is 4. So the reason why that would be the strongest acid would be, if you see this hydrogen, it is very easy to snatch off that proton because it is attached to oxygen first, like this one, but furthermore, it has a carbon double bond oxygen O. So this is actually called carboxylic acid. These are actually pure acids. In terms of the definition, they are called carboxylic acids. Carboxylic acids in general range between 3.8 to 5. These are carboxylic acids. Carboxylic acids. So remember to understand, not by memorizing each number, but by just looking where the protons are attached to. So there are no many compounds and many combinations. As I already told you, something which is attached to a carbon-carbon triple bond is about 25. Something like alkane is the weakest acid, which is with pK value of 50. Something which is attached to a nitrogen, meaning nitrogen like this, are around 38, 40. Something which is only attached to one oxygen, they are called alcohols. We'll review those in the future sections. They are a pK of 16, 17, up to 18. So carboxylic acids, as you see, are attached to one oxygen, and that oxygen is attached to a carbon that is double bond oxygen. So they are generally called carboxylic acid. So no matter whatever you have here, as long as the carboxylic acid unit is this unit, right? This, if you have something like this, mostly in textbooks they write them Br CH2 CH2 COOH. So this is another way of writing it, COOH. So that proton is the strongest in terms of scale. They are ranging from 3.84 to 4.5 to 5. So this is the concept, how to read the pKa tables and to compare qualitatively what the pKa values for organic acids are. But another important concept also, once the acids dissociate and give off their proton, they always form a conjugate base. So strong acids always generate a very weak conjugate base. Cl- is conjugate base, which is very weak as a base. But if you just look at this metal minus, this is after removing this proton, which is a very weak acid, and if you succeed to take off that proton with very, very strong base, and you generate this is the strongest base, conjugate base. Conjugate base. This is the weakest conjugate base. So the scale goes down, actually increases like this. Strongest conjugate base is this. Here, the strength of the acid increases that way. So a strong acid generates a very weak conjugate base. A very weak acid generates a very strong conjugate base. Okay, here we'll be discussing reaction equilibrium when you have an acid and base, and predicting which direction the equilibrium would shift. That means whether it goes to the right or to the left. So this can be done just by knowing the pKa values of each one of the reactants in the reaction. So in principle, this is the rule that you would apply. In principle, when a chemical reaction happens, it doesn't produce the strongest acid, for example. It should start from a strong acid from left side, for example, and produce as a byproduct a weak acid, not the reverse. You cannot always produce in a chemical reaction for the reaction to be favored. You are always generating a weaker acid or a weaker base. So let's evaluate each of these reactions. Starting with A, for example, you have hydrochloric acid with pKa value and a base, sodium hydroxide. The sodium hydroxide, which is OH minus, would abstract one of the protons, one proton here, producing water and sodium chloride. Obviously, this is a strong acid, base, strong base. This is a conjugate acid. This is a conjugate base. So if you look at here, the pKa values are -7 is for hydrochloric acid, very, very strong acid. So from -7, it is going to 16, a very weak acid, which is water, around 16. So this reaction actually is favored in the forward direction, in the right direction, but very little equilibrium to the left. So reaction A, which is a reaction between hydrochloric acid and sodium hydroxide, almost completely goes to the right side, because the pKa value difference is such that this is a very strong acid and you are generating a weak acid. Like I said earlier, the rule is when you do the reaction, you have to go from a very strong acid to a very weak acid. Otherwise, the reaction would go to the reverse direction. For example, here we have two. One is a base. Obviously, a base is where you have a lone pair of electrons that can abstract a proton from an acid. like I said, acetylene with sp hybridized carbon has a pKa value of 25. So one of the protons from acetylene, that is the hydrogen on the acetylene carbon, which is this one of those, when it is abstracted by NH2 as a base, this is a base, this is the acid now, this is the acid, this is a base. So what are we generating? So when a base is abstracting a proton here, you are creating this conjugate base, and a conjugate acid. So let's evaluate now a pKa value of 25 for acetylene, and the acid that is generated is pKa value of 38. So from a very stronger acid than NH3, therefore the reaction actually favors the right direction. So most of it is in the right direction. That's why the two arrows are not equal now. So most of it is the reaction is favored in the right direction. Okay, let's reverse and let's see this reaction C, for example. In reaction C, you have acetylene still with a pKa value of this hydrogen to be 25, and you have a base. So let's call this is a base now. You should remember the base is where you have a greater number of lone pairs of electrons, or a fully charged species. That would always be the base. Here it is an acid. So now we classified acid, our base. What is our conjugate base as a product? As a product, what happens is this oxygen picked up one of the protons to become ethanol, or this compound, and the remaining was this, because one of the hydrogen has been taken off. So here we are going from an acid to another acid which is more stronger, because this is 25, that is 16. This is a strong acid. This is the acid form. So it's all is relative in the reaction. This is the base, the conjugate base. Here is a conjugate acid. Now in this reaction, as it is written, the reaction wouldn't favor the right direction, because you start with a weak acid and you are generating a very stronger acid than what you started with. Therefore, the equilibrium actually doesn't favor to the right direction. It actually favors the left direction, very little into the forward direction. So in predicting the acid-base equilibrium, you need to always understand the pKa differences that your reaction creates in the right direction and in the left direction. So here, it's very easy to predict the reaction actually goes to the left. This means it's not going to the right direction. So the reaction actually doesn't happen. Now, in reaction D, what I did is I reversed exactly this as a reactant. Therefore, I think the reaction should go. Let's see here. Our conjugate base, the base is this now, because you have a lone pair of electrons on carbon, that is a hybridized carbon. It can carry the negative charge very easily. Now you have a pKa value of 16 for this, because that hydrogen is on oxygen. Remember, in general terms, we have outlined what the pKa values look like for such compound. It doesn't matter whatever extension you have, but as long as it is on oxygen, approximately it would be 16. Now you have the conjugate base that is created, and you have a conjugate acid that is theoretically formed. So now what did happen? So the reaction actually is from 16, which is a stronger acid with pKa value of 16, it goes to a weaker acid with pKa value of 25. Therefore, The equilibrium is right in the right direction and very little to backward direction. So the reaction can happen. So if you were to be asked which direction the reaction happens, this is how you would put the arrows differently in different instances by evaluating the pKa differences in each compound. Therefore, I want to summarize by saying that all reactions should lead to a weaker acid than what you started with. Therefore, the conjugate acid that's formed cannot be stronger than what you started with to predict the reaction direction. It also applies for a base. If you have a base that you started with, if it was a weaker base, you cannot generate a very strong base in that direction. So this applies for both of them, for acids and base reactions. Right now, what we evaluate was with the values that we already have as a pKa table for the acids, and we were able to predict which direction the reaction can happen.